We give the definition of Graphon filters and give their frequency response. We further show that the frequency response is independent of the Graphon itself. Every Graphon W induces a Graphon shift operator TW. By recursively applying the Graphon shift operator to a Graphon signal, we can create a diffusion sequence with the kth element of that diffusion sequence, TWKX, given by the integral evaluated between 0 and 1 of the product between the Graphon W and the previous element in the diffusion sequence. For this definition to be complete, the initial term of the diffusion sequence has to be defined as the signal X itself. We can now use that diffusion sequence induced by a Graphon shift operator to define a Graphon filter. Formally, we say that a Graphon filter of order K is defined by the filter coefficients Hk and produces outputs Y given by the sum up to order K of the product between the coefficient Hk and the kth element of the Graphon diffusion sequence TWK of X. A Graphon filter maps a Graphon signal X to another Graphon signal Y. Relying on our standard notation for operators, we then denote a Graphon filter by THX. Note that a Graphon filter is nothing more than a linear combination of successive Graphon diffusions of the original signal, TWK of X, modulated by the corresponding filter coefficients Hk. In this sense, a Graphon filter has the same algebraic structure of a graph filter. As we saw in previous lectures, a graph filter can be defined as a polynomial on the graph shift operator. That is, a graph filter of order K is comprised of successive graph diffusions up to order K, modulated by the corresponding filter taps, whereas a Graphon filter of order K is comprised of successive Graphon diffusions, represented by recursive applications of the Graphon shift operator TW, also modulated by filter coefficients Hk. The only difference lies in the shift operator. Instead of a graph shift operator, we now rely on the integral Graphon shift operator TW of X instead. To construct the output of a Graphon filter, we start with the input signal X, which, when modulated by the initial filter coefficient H0, will be the first element used to construct the output. We then apply the Graphon shift operator TW to the input signal, observing the first diffusion of the Graphon signal given by TW1 of X. That quantity is scaled by the corresponding filter tap, H1, which will be summed with the previous element in the sequence to construct the output of the filter. By another application of the Graphon shift operator, we now obtain the third element in the diffusion sequence, TW2 of X, which is modulated by the corresponding filter coefficient H2 and added to the previous components of the output. By yet another application of the Graphon shift operator, we now observe the fourth element of the diffusion sequence, TW3 of X, which is then modulated by the corresponding filter coefficient H3 and added to the previous components to construct the output Y of the Graphon filter. Here, we have a filter of order 4, but the process is essentially the same for higher order Graphon filters as well. Now, we'll leverage the Graphon Fourier transform to analyze Graphon filters in the frequency domain. First, we compute the Graphon Fourier transform of the input signal x hat, with each component x hat j given by the integral of the product between the signal x and the jth eigenfunction, phi j. The Graphon Fourier transform of the output y hat is defined in a similar manner. Now we state a theorem for the graph frequency representation of Graphon filters. According to each given a Graphon filter th with coefficients hk, the components of the Graphon Fourier transform of the input and the output signals are related by the following expression. That is, the jth component of the Graphon Fourier transform of the output, y hat j, is equal to the product of the jth component of the Graphon Fourier transform of the input signal, x hat j, and a polynomial on the jth eigenvalue of the Graphon shift operator, TW, modulated by the filter coefficients hk. That is, the same polynomial that defines the Graphon filter, but with the eigenvalue lambda j and not the Graphon shift operator as a variable. Since the jth component of the Graphon Fourier transform, y hat j, depends only on the jth component of the Graphon Fourier transform of the input signal, x hat j, and a polynomial on the jth eigenvalue, we can conclude that Graphon filters at pointwise in the Graphon Fourier transform domain, in the same way that graph filters at pointwise in the graph domain. That pointwise characteristic of Graphon filters in the Graphon Fourier transform will allow us to define the frequency response of a Graphon filter. Given a Graphon filter with coefficients h, the frequency response of the Graphon filter is defined as a polynomial on the scalar variable lambda modulated by coefficients hk. This is exactly the same definition of the frequency response of a graph filter with the same coefficients. As we have shown, the frequency response of a Graphon filter and a graph filter are the same if they share the same filter coefficients. Both the frequency response of a Graphon filter and the frequency response of a graph filter are polynomials modulated by the filter coefficients, with the Graphon filter instantiating Graphon eigenvalues and graph filters instantiating graph eigenvalues. It does not matter if the graph sequence converges to the Graphon or not. The filter transfers either way, as we will discuss with more detail in the next sections.